Okay, so here is an extremely high-powered flyback driving setup. Here we have our ZVS driver. This is originally supposed to be an induction heater driver. So you can see it has features to help it handle more current, such as cooling and extremely thick traces on the PCB. And here we have our ZVS flyback connected to our leads where we'll be drawing some sparks. And it's powered by two 12-volt power supplies in series that can each output 30 amps. But we actually have the dial turned all the way, so they're both hiked up to 15 volts. So in total it's 30 volts at 30 amps. And let's turn it on and see what kind of sparks we can get. So these are some massive sparks, and I can actually feel the wind from the ionization on my hand. It's kind of a cool breeze almost. It's interesting. And it looks like we've blown something, which is expected when you're trying to run a induction heater for a flyback. I hope you enjoyed that. So it ended up being just a safety feature that tripped on one of the power supplies. So I'm going to quickly demonstrate what I mean by high frequency output and why this is so important. So I have just a much smaller voltage going into the driver now, only 10 volts. And as you can see, the spark is a lot smaller. And then here is our oscilloscoped output, and this is the input into the flyback. So as you can see, it's around 63 volts, but the crucial thing to see here is the 40 kilohertz. And this is what makes the ZVS driver so efficient compared to other drivers, is that it can produce an efficient current at such a high frequency. And the reason that you want high frequency is because when dealing with inductance and transformers, the higher the frequency, the more efficiently the energy is transferred. So here we have our step-up transformer, which is very few turns with thick wire around a ferrite core, and that directs the field lines through here to our secondary, which is, I would say, a couple thousand turns of very thin copper wire, and then that leads to our output. So we step our voltage up from 60 volts to several thousand volts. So a couple more things to note here is watch what happens to the waveform when I connect the electrodes or generate a spark. So as you can see, I'm actually changing the frequency slightly. And then the second thing to note is here we have our blue probe, and you can see the blue waveform there. And you can see it's less than a volt, and that's just because it's floating in the air. But since this is such high voltage, and we have such a large amount of energy, and we're creating such a large magnetic field, even at such a small input, watch what happens when I move the probe closer to the high voltage. You can see the waveform is starting to rise, and even just setting it here, the waveform is already almost unreadable by the scope. Okay, so I've reconnected both the power supplies again, and now instead of the flyback transformer, we have our induction heating coil. So I'll go ahead and turn it on, and as you can see, we're back at 30 volts and 30 amps. And so this is running right now. and as you can see, it's not hot at all. I can completely hold this. However, when we put a screw in here, you will begin to be able to see it get hot very shortly, and it should get to the point of being red hot. I've also reconnected the scope here, and you can see that we are running at around 95 volts for the output, and you'll also notice that the frequency is higher than it was before, just because the parameters of our coil are different. This is an air core, and it's quite larger with actually roughly the same amount of turns, but just because the parameters are different, it's going to give us a different oscillation frequency for this circuit. So I'll go ahead and turn off the lights and see if we're starting to get red hot. And as you can see, the screw is actually starting to glow because that's how hot it's getting. But the whole time I can actually touch the coil. So if this were a stovetop element, it would be completely safe to have it running because it wouldn't get too hot to touch unless a pot was on it. And this is why induction ovens are so much safer than standard element ovens. So as you can see, this screw is obviously very hot now, and the reason that it gets hot is because of something called eddy currents. And basically what's happening is, since this is such high frequency and such high current, the magnetic field is rapidly changing back and forth at a massive amount and a massive rate. So all the atoms inside this metallic object are circulating back and forth, and just that extra energy of moving back and forth and bumping into each other is creating the heat that you see here. So thanks for watching. I hope you learned something new about ZVS drivers and why they're such efficient and useful induction drivers.